Hi. So no lecture today, it's just Monday. You've been doing a really great job exploring groups in last week's tutorial, and I just wanted to do a quick demonstration to help out with that. So I'd like to talk about a family of groups that are called the dihedral groups. And this is a family that includes a lot of the different groups that people have been finding, on your own. So I'm going to look at two of these. And the groups that I'm looking at are the symmetries of certain shapes. So here I've got my equilateral triangle, and here I have a square, just some CD drive. In general, the dihedral group D sub n is the group of all symmetries of a regular n-sided polygon. So 3, you get a triangle, 4, you get a square, 5, you get a pentagon, and so on. But they all have similar properties that we can explore through example. And just as a caveat, I'm calling them, D3, D4 here for my purposes because that name makes a lot of sense for me. Other places use different names for them because they stink. So if I'm looking at my triangle, this is my labeled triangle, so I've got points 1, 2, and 3, there are going to be 6 different symmetries. So I'm going to say that the symmetry R is for rotation. So my symmetry R says rotate anti-clockwise by 120 degrees. And I can rotate again, I'll get some new symmetry. And if I try R cubed, right, rotate, 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 I get back to where I started. If I want to think the same way with the square, instead, I need to rotate by 90 degrees, right? So I can do R, rotate by 90 degrees. I can do R squared, that's rotating by 180. R cubed is rotating by 270, and R to the power 4 is a rotation of 360 degrees. So this is for the 3-gon, the triangle, and the 4-gon, the square. If you are looking at an n-sided polygon, then your rotation R is going to be a rotation of 360 divided by n degrees, right? So that way we can make that formula work no matter what shape you pick, as long as it's a regular polygon. So that's half of the symmetry group. The other half are the flips. And here is why I need to have 2 examples, because the flips work differently if you have an even number of corners or an odd number of corners. So here I've got my triangle, and there are 3 flips. I can keep 1 in place, so there's a flip. I can flip back. I can keep 2 in place. There's a flip, and there's a flip back. And I can keep 3 in place. There's a flip back. So I've got 3 rotations, identity, rotate 120, rotate 240. Get back to identity. And I have 3 flips. So hold 1, hold 2, hold 3, and that's all 6 symmetries. And that's for, in general, if I had some polygon with n sides, I'd have 2 times n symmetries. Like I was saying, it's a little different for an even number of corners or an even number of sides. So here I've got my square. If I fix this corner, then I also have to fix this one, right? My flip is going to go diagonally. And if I fix this corner, then I've also got to fix this one. So I've got, here's 1 flip, here's 2 flips, but that's not all of them. So if you have an even number of sides, you'll have parallel edges, which you don't get on the triangle or any other odd number of vertex polygon. So I can flip and keep my vertical sides the same, right? And I'll just flip like that. All 4 of the vertices moved, but the sides stay in place. I can do that the other way too. I can flip this way, the top and the bottom stay, and now all 4 corners move like that. So it'll be a little bit different where the flips are. On an odd numbered polygon, every flip is from holding one corner and then the opposite side, like this. On an even numbered polygon, you'll either hold 2 opposite corners, there'll be n divided by 2 of those, right? One for every pair of opposite corners, and another flip for every opposite pair of sides. So there'll be some flips that are holding 2 sides in the same place. So either way, whether n is even or odd, there will be 2 times n number of symmetries. And that'll be for any n at least 3, because 3 is the smallest polygon. There's no such thing as a two-gon for our purposes. So the last question then is, will this group be abelian? And I am posting this video to tell you all that the dihedral group is always non-abelian. There are certain symmetries where the order that you perform them changes. So here is my triangle. And again, R is going to be my rotate by 120 degrees. And there's R again. And a third R gets me back to identity. And I'll use the element F for flip. So I should be putting an equation on the screen right about now. If I do a rotation first, and then my horizontal flip, then my vertex number 1 that was up here at the top is now down here at the bottom, right? So let me undo that. We start up here at the top, we end up down here at the bottom. What happens if I do the horizontal flip first and then the rotate by 120 degrees? So I will flip first, and now I rotate, and this time the number 1 vertex ended up over here instead. So I get a different symmetry. So I can flip back like here. If I do the horizontal flip first and then the rotate, it's as though I just held on to this number 2 corner and did my flip here. So the formula for this is going to be up on the screen now. If we do RF, right, so a rotation and then a flip, it's going to be the same thing as flipping first and doing the opposite rotation. So algebraically, RF equals FR inverse, right? I'll have that up on the screen. So that's true no matter what shape we're looking at, as long as we're looking at one of the dihedral groups. So I can do that on my square as well. So let's follow this vertex in particular. If I rotate by 90 degrees and then flip, the vertex that I'm following is down here. Let me put that back to normal. I claim if I flip first, I have to rotate the other way, right? I have to do flip and then rotate backwards to get the same symmetry that I saw the first time. That is a true statement for every single dihedral group. All right, cool. This has been fun. I will see you tomorrow for a full lecture.